Now, let's prove theorem number 4, which states that when two sides of one triangle are proportional to two sides of another triangle and the included angles are equal, then the two triangles are similar. Now, let's prove it. Given triangle ABC and triangle DEG with DE with DE over AB is equals to DG over AC, and angle A equals to angle D. So obviously we are given triangle APC and triangle DEG with that over that equals to that over that. And we are given this is equals to that, because the theorem tells us that when two sides over that of a triangle are in proportion and the included angle between the sides which are in proportion are equal, then the two triangles are similar. Therefore, this is what we are given. To prove that angle B is equals to angle E and angle C equals to angle G. This is what we are to prove, because we know that this angle is equals to that angle. This side over this side is equals to this side over that side. Then we just need to prove that this angle is equals to angle that, this angle is equals to angle that. Now, construction. We construct like we did in theorem number 2 and 3, where we draw HI such that AH such that AH is equals to DE, and AI is equals to DG. This such that this is equals to that, this is equals to that. Now, if you've noticed in theorem number 2 and 3, we needed to prove that this triangle is congruent to this triangle. And even with this proof, we still need to prove that this triangle is congruent to this triangle. By congruent, I'll repeat that it means that they are the same. So we need to prove that this triangle is the same as this triangle. They are congruent. Therefore, proof. Now, proof in triangle AHI and triangle DEG. H is equals to DE. Construction, risen, we have constructed. Also, angle A is equals to angle D. We were given that. Obviously, we were given that here. Now, AI is equals to DG. Also, risen, construction. Therefore, triangle AHI is congruent to triangle DEG. Now, since the two triangles are congruent, this means that since these triangles are the same, the two triangles are the same, it means that A angle HI, which is this angle there, therefore, A angle HI is equals to angle E. And A angle IH is equals to angle G. Therefore, this angle is equals to this angle. This angle there is equals to this angle. Since the two triangles are equal or are congruent. Now, since we are given that, but DE over AB, but we know what is DE. DE is AH. So we can just write AH over AB is equals to our DG, we know is AI. So we can put AI over AC. We've just wrote this there, but we have replaced DE and DG by HI and AI respectively. So why is that? Because we've got construction. The reason for that. Now, since AH over AB is equals to AI over AC in triangle ABC, then we know that this side is parallel to that side. Therefore, HI is parallel to BC. Why are they parallel? Because segment drawn parallel to one side of triangle. Segment drawn parallel to one side of a triangle. Obviously, if a segment is drawn parallel to one side of a triangle, or segment divide, because here we're talking about the converse. Segment divides, sides, divide sides, proportional, in proportion. This line divides sides in proportion. You can see this line, that is why, that's the reason. segment divide sides proportionally. That's the reason why this is parallel to that. It is because of that, because we've got sides which are in proportion in a triangle. So it means that this side is drawn parallel to this side. Now, since this is parallel to that, we know from part 1 that this angle is going to be equals to this angle there. Therefore, angle B is equals to corresponding angle B is corresponding with A angle H I, and which this is equals to that. We know it is equals to that, since this triangle is equals to this triangle, since they are congruent. Therefore, it is equals to that, which is equals to angle E. And angle C is equals to corresponding with A angle I H, which is equals to angle G. Here is the same thing as I know this is another way of writing corresponding angles, but we could have said angle B is equals to A angle H I. Then we give a reason that corresponding angles, why are they corresponding? It is because HI is parallel to BC. For this, even for that, we could have said angle C is equals to A angle I H, and give the same reason, corresponding angles HI is parallel to BC. But I just used a new style where angle B is equals to corresponding angle A angle HI, which obviously here we could have said this is equals to angle E. We could have also said this is equals to angle G. If we wanted, we could have wrote this in a way that we are used to write it. But this is another way that we can write corresponding angles, by giving the reason with the angle. Therefore, angle B is equals to corresponding A angle HI, it corresponds with A angle HI, which is equals to angle E. Angle C is equals to, is corresponding with A angle IH, which is equals to angle G. Therefore, triangle ABC is similar to triangle DEG, because this angle is equals to that angle, this angle is equals to that angle, and we were given that this angle is equals to this angle. Therefore, it means that we've got equiangular triangles. We can give the reason there to be equiangular triangles. They are similar. Now, let's state theorem number 5 and prove it. Theorem number 5 states that the square in a right angle, the square of the hypotenuse side is equals to the sum of the squares of the other two sides. Let me repeat that. Pythagoras Theorem, which is theorem number 5 in grade 12, states that in a right angle, the square of the hypotenuse is equals to the sum of the squares of the other two sides. Now, let's prove it. What I've just said is that Pythagoras theorem states that the hypotenuse side, which is always opposite 90 degrees, which is the longest side. Therefore, the square of the longest side, or the square of the hypotenuse, which is the side opposite 90 degrees, is equals to the sum, is equals to the square, the sum of the squares, the sum we mean by adding the sum plus. So it means that the square of the hypotenuse is equals to the sum of the squares of the other two sides. The square of this is equals to the square of this plus the square of that. That is Pythagoras theorem. Now we want to prove Pythagoras theorem. We want to prove that this side is equals, this side squared is equals to this squared plus this squared. That's what we want to prove in this theorem. Now, given triangle ABC with angle A, with angle A equals to 90 degrees. To prove that, BC length, BC squared is equals to AB squared plus AC squared. We are given triangle ABC, which is a right angle triangle. We are to prove that the longest side, which is the hypotenuse, is equals the square of the hypotenuse is equals to the square of the other two, the sum of the square of the sum of the square of the other two sides. Now, construction. We construct AD, draw AD perpendicular. We must draw AD perpendicular to BC. Therefore, there is AD perpendicular to BC. There's your D there. I've just drawn AD perpendicular to BC. That's our construction. Now, for us to prove that BC squared is equals to this squared plus this squared, we need to get this side squared and get this side squared, then add the two sides which are squared so that they can give us this side squared. But how do we go about that? We are going to use similarity. We are going to use equiangular triangles. And by using equiangular triangles, for us to get AB in terms of this, and that, for us to get AB in terms of this and that, we need to first prove that this triangle is similar to this triangle here. For us to get AC, we need to get this squared in terms of this and that. Sorry, in terms of this and that. Let's repeat that. For me to get this side, I need to write this side in terms of this and that over that. For me to get this side, I need to get this over that as well. But I must first prove similarity for me to get this side in terms of this over that. Let's see that. Proof. In triangle BDA and triangle ABC and triangle, and triangle ABC, we can see that B angle DA, which is this angle, 90 degrees, B angle DA, this angle is equals to this angle. So in this triangle, I've got 90 degrees. In this whole triangle, I also have 90 degrees there. Therefore, it means that B angle AD, which is this angle there, is equals to this angle there, which is B angle AC, is equals to B angle AC, which is equals to 90 degrees. Why are we saying that? That is because we're given that. We're given that angle A is 90, and we're told to construct in such a way that this line is perpendicular to that line. So we're given. Now, we now know this angle is equals to that angle in this triangle. We are proving that this triangle is equiangular to this triangle there. Therefore, it means that angle B is equals to angle B, because this triangle and this triangle, B is common. Therefore, angle B is equals to angle B risen. B is common. Now, since we have shown that this angle is equals to this angle for the two triangles, because this triangle and this triangle share B. They share this angle. Therefore, that is why we say angle B is equals to angle B, which is common. Now, B angle AD, which is this angle there, this angle here. Obviously, this angle is going to be equals to C, because this angle is in this triangle, which is this angle, will be equals to this angle C there. Therefore, B angle AD, B angle AD is equals to angle C risen. Since we know that this angle is equals to this angle is equals to 90, the last angles in these triangles will be equal, obviously, because sum of angles on triangle, sum of angles of triangle, sum of angles of triangle, sum of angles of a triangle are supplementary. sum of angles of a triangle are supplementary, because we know this angle is equals to this angle is equals to this angle in this triangle, and this angle obviously is going to be equals to this angle. And the reason that I gave the last time is third angle of a triangle. Third angle of a triangle, if I wanted, I could have said third angle of a triangle, because that's the third angle, which it will be equal, obviously, since the two, this angle is equals to that angle, this angle is equals to this angle. Therefore, the last angle of these triangles are going to be equal. Therefore, therefore, I'm just going to write it above. Therefore, triangle BDA is similar to triangle ABC. Reason? Equiangular triangles. Equiangular triangles. Since this triangle is similar to this triangle, then we can say that AB, therefore, AB in this triangle and AB in this triangle is opposite 90 degrees in this triangle. In the bigger triangle, the side which is opposite 90 degrees is BC. That is why we say AB over BC is equals to, let's repeat this. AB in this triangle, which we've just proved that it is similar to this triangle. AB, since it is opposite 90 degrees in this triangle, we want the side which is opposite 90 degrees in this triangle. Therefore, it is BC. That is why we said AB, which is opposite 90, over BC, which is also opposite 90, is equals to, now, this angle here in this triangle is BD. BD, but obviously this angle in this triangle, we need to look at the side which is opposite this, the equal angle for this triangle. And we've said that this angle is equals to that one there. Oh, so this angle is opposite this side there. Since this angle and this angle are equal, and this angle is closed by BD, this angle is closed by AB, then we're going to say BD, which is closed by this angle, over AB, which is closed by this angle, since the two are equal. So it is closed by this side over AB. Now, when we cross multiply this times this, we get AB squared is equals to this times that is BD times BC. Okay, so we now got this, like I said, in terms of this over that. You can see AB is equals to this times that is equals to this times that. That is why we have that. And it means that this side is going to be equals to this times this. Similarly, we can prove that triangle ADC is similar to triangle ABC. As you have seen, we have proved that this triangle is similar to this triangle. Then we got this side. We can also prove that this triangle is similar to this triangle, so that we can get this side. But no need for us, we now know that, we can do a similar thing to prove that this triangle is similar to this triangle. Therefore, we can see that we can get this side, which is AC, over my AC for this triangle, since it is opposite 90 degrees, that is why I say AC, but I must look at the side for this triangle, since this and this are similar, since this triangle and this triangle are similar, and this side is opposite 90 degrees, this side for this triangle is opposite 90 degrees. So since this is opposite 90 and this is opposite 90 in the two triangles, then I'm going to say AC, which is opposite 90, over BC, which is opposite 90, over BC, is equals to. Now, I can look at this angle there and this angle. I know that it is equals to this angle there. Since I've started on this triangle here, which is, I must take this side because there's your triangle, which is similar to this triangle, and this angle is equals to this angle. Also, it means that since for this side, I've started on AC over BC. On this triangle, I started by AC, which is opposite 90, over BC for this triangle, opposite 90. That is why I've got AC over BC is equals to. Now, since this angle is equals to that angle there, then since I started on this triangle, I still need to start on this triangle. So I take this side, DC, over. So this side is opposite this angle, and this angle is equals to this angle there. So it means that I must take this side for this triangle, which is AC. I repeat for the last time. Since this side is opposite 90, I say AC over. Since for this triangle, then I say AC over. For this triangle, which is that, since they are similar, over BC, is equals to, I look at this angle and this angle there. Now, I started on this triangle, this side, so it means that I'm going to say, since this angle is equals to this angle, for this triangle, I'm going to say DC there, over, for this triangle, I know this is the angle which is equals to that. Therefore, it means that I'm going to say over this side for this triangle. That is why I've got AC over BC is equals to DC over AC. Now, I cross multiply again here. This times this, I get AC squared, which is equals to this times this is DC times BC. Oh, this is nice. Wow. Now, since this is nice, I can see that I can add the 2 because I know I want to prove that AP squared plus AP squared plus AC squared. You see, I want to prove this, that it is equals to that. So I already have this side, which is equals to this times that, and I also have this side, which is equals to this times that. Therefore, a b squared, plus ac squared is equals to, so I'm adding this plus this, there, this side, there, this side, this is this side of the equal sign, therefore I'm adding them, ap squared plus ac squared. Then I add what's that side, so I'm going to add bd times bc plus, obviously I'm adding with this as well, dc times bc. Can you see that? Now, here I've got 2 terms. I can take out bc because there's bc here, there's bc there. So I can take out bc, I take out, I'm going to be left with bd here plus dc because I took out bc. I took out bc outside. In this term, I'm left with bd plus, in this term, I'm left with dc. There's my bc. I've factorized this part there. I've took out bc because it is there and there. Our factorization, we must be good with that. Now, what is bd plus dc? bd plus dc. It is the whole of bc. Oh, so it means that here I've got bc times bc. Oh, so this bd plus dc, this is bc. Because when I add this plus this, I get the whole length. That is why it is bc, this part. Therefore, bc times bc, it is bc squared. Therefore, ab squared plus ac squared is equals to bc squared, which is what we were supposed to prove by Pythagoras Theorem. We could have shown that ADB triangle ADB is similar to triangle ACD. And theorem number 4, we've just shown that this is similar to that. We also showed that this is similar to that. We can also show that this is similar to that, so that we can get this side in terms of this side and this side. Triangle ADB is similar when triangle ADB is similar to triangle ACD. Then we can find that AD, which is opposite this angle. Oh, so since it is opposite this angle in this triangle, AD, so we must look at the side in this triangle that is So it means that it is going to be over DC. Because AD in this triangle, since they are similar, this triangle in this case is similar to this triangle. Since they are similar, this angle is equal to that angle. So it means that AD over BC is equals to, I can also look at this angle here and this angle there. But since I've started in this triangle, so it means that I'm going to look at this angle, which I'm going to, with green, and this angle there. Therefore, you can see that since I've started in this triangle with this angle, where I said AD over, since it is equals to that, DC, it is going to be equals to BD, since this angle is opposite this side. It's going to be equals to BD over this side, this side, this side. Because I'm looking at these two triangles. I can't go to that triangle now. So it means that I'm looking at these two triangles. So this angle is opposite this side in this triangle. This angle is opposite this side in this triangle. Therefore, that is why I'm going to say BD over AD. Over AD. Therefore, you can see that this times this is AD squared, which is equals to this times this is going to be equals to BD times DC. Oh, so it means that, when a perpendicular line is drawn from the 90 degrees vertex angle, if a perpendicular line in a right angled triangle, if a perpendicular line is drawn from the 90-degree vertex angle, then we can conclude that when triangle ADB is similar to the whole triangle, when triangle ABD is similar to triangle ABC, we have that AB squared is equals to BD times the whole of this BC. If this triangle is similar to the whole triangle, this is what we have for AB. If triangle ADC is similar to triangle ABC, we have that this side, which is AC squared, is equals to this, which is DC, times the whole of this, which is BC. So it means that if triangle ADB is similar to triangle ACD or ADC. So if this triangle is similar to this triangle now, then we have that AD squared, which we've just got now, AD squared, which is we just got now, is equals to BD times BC. DC, sorry, times DC. What are we saying exactly? We are saying that if we can draw a perpendicular line from the 90 degrees vertex angle, and if we have triangle ABD or ADB to be similar to the whole triangle, if this triangle is similar to the whole triangle, then AB squared is going to be equals to this times that. If this triangle is similar to the whole of this triangle, then we're going to have AC to be equals to this times that. That is why you see that here. If this triangle is similar to this triangle there, then we're going to have AD to be equals to this times that. It's just as simple as that. The converse of Pythagoras theorem, obviously the converse is the opposite. And Pythagoras theorem tells us that in a right angle triangle, the square of the hypotenuse or the square of the longest side is equals to the sum of the square of the other two sides. Its converse or its opposite, it tells us that if the square of the hypotenuse is equals to the sum of the square of the other two sides, then we know that that triangle is a right angle triangle. That is why we say that the converse is the opposite, because if we are given a right angle, then that's Pythagoras theorem. If we are given a right angle triangle, then the square of the hypotenuse is equals to the sum of the square of the other two sides. But its converse is that if the square of the hypotenuse is equals to the sum of the square of the other two sides, then we know that that triangle is a right angle triangle.